Hey everybody, this is Larry. This is me over Q4 of the weekly contest 481. Total sum of interaction costs in tree groups. Hit the like button and subscribe button, join me on Discord. Let me know what you think about this one. Yeah. So first thing first, during this one I was very annoyed that they called interaction costs because they define interaction costs and it's just the distance. So it is just the distance, except for because they don't even use it in the order, like they don't use it in the context of the groups at all. They just kind of like, oh, this is the interaction cost, which is the distance, by the way. Even though distance sometimes mean a couple of things in a tree for whatever reason, some people define it or like for some. I know that it has a precise definition, but some definitions are just like very basic, right? Meaning that for some problems it's defined as the number of edges, for some other problems it's defined as the number of nodes. For a tree is not that big of a differentiator because the number of nodes is just the number of edges plus one. Anyway, little bit of a side rant aside, interaction cost is still such a weird thing that I was like, did I read this correctly? Because it slowed me down in the reading because I was just like, well, if it's a distance, why would they call it interaction cost? Turns out it's just basically code things. It is what it is. All right, so yeah, the key thing that I know, I was thinking about different ways of doing it. Honestly, I was thinking of maybe DP and maybe tree rerouting, something that we talked about. For me anyway, very recently, because it was on a contest very recently. But again, everything about rerouting is just about geometry and this idea of drawing things out. We'll go over it again in a second. But I was like, well, I don't know how to handle the group part, right? And then the next question I asked myself was like, well, what is it about groups that prevent us from handling it? Well, it's just that there's so many different groups, and if you have to solve it once per group, then it just can become n squared. And then I scroll down, I look at the constraints, and it said groups is equal to 20, and I'm like, okay, well then I guess I already have the answer. I still took a long time to implement. Actually, wow, a long time actually, due to just like some off by ones and correctness and stuff like this. Honestly, it probably should not have taken me this long. I'm still like, I'll practice on tree rerouting. It doesn't really come up that much, but then it came up like twice in the last couple of contests. I don't know. But how did I feel about it? I don't know. But yeah, but it's not so bad. I think the idea, and this one, especially the sum of distances, seems like one that would be pretty straightforward, or at least pretty, like it probably is amounts to first tree rerouting problem that you really solve. And as a result, then this is not that hard of a hard. But there's a lot of assumption in that idea, right? Meaning that assuming you already know the algorithm and assuming that you practiced it, then yeah, it's not that hard, which is, well, you could say that about a lot of things probably. But that said, inversely or maybe conversely, man, today I'm not 100%. But the other way is still kind of true, right? Which means that if you don't know tree rerouting, this may not be that possible because I don't know. I mean, maybe there's a DP way, but yeah. So the way that I did it is for each. I'm gonna call it group colors just because whenever I have trees or just graphs and nodes and graphs that have like different groups, I always just call them colors because it's just easier to visualize in my head. So yeah, so I think there are at least two ways to write this, right? I didn't look for all the solutions or whatever, so there may be more, but at least the two off my head. One is the way that I did it, which is that we solve it once for each color from the root, and then the other is you solve them all at the same time with all the colors passing back and forth, which both are basically equivalent. It's just about doing it at the same time or doing it separately, but each of them has the same cost. So yeah, I guess technically if you do them separately, it would have a higher max memory usage, which may or may not come in as an issue for this one, but just something to know. Okay. Oh, before I actually go into code, I like to draw this visualization. Maybe I'll draw it a couple more times before I just take it for granted, which I don't know. Maybe I just need a video for this, and then just tell people to watch that video. I don't know. Let me know in the comments if you're watching this, and what do you think about this. But in essence, the tree rerouting algorithm is actually pretty simple because it's all about geometry, right? Basically, we do two passes, two traversals of the tree. So the first traversal of the tree, that's it, and I kind of always draw binary because it's just more native, I don't know, natural maybe, or just common. I don't know, muscle memory, right? So basically, you do one pass where each node stores the answer to a subtree, right? So that means that this is just by itself because it is the leaf, but then here would contain the answer that is for this node subtree. This one would contain this node, and so forth, right? Okay, so then now we established that for each node. So this is just the first pass. It's very basic. It's not going to give you the answer because, well, you only have it for the subtree. You don't have the rest of the tree. Okay, right? But we already established that, and this is for every tree rerouting problem, not just specific for this one. We'll go over things that are specific for this one in a little bit. But okay. Right? Yeah, so you have this tree node, so that means that for every node, you have this answer, right? And basically the idea for tree rerouting is that, okay, well, now we're trying to figure out the rest, right? So we're trying to figure out this part, which it doesn't have, right? And maybe I tend to draw it too high up. Maybe this is a better example, right? So we have this. So then now we're trying to figure out the rest of this tree so that we can combine it in a way to get the real full answer for this node, right? And then after this, the beauty of this, at least for me, even though it took me a while for this particular problem, is just it's all visual. And the way that I visualize it is basically how I'm drawing to you now. I'm just going, okay, well, so this is what I'm trying to solve. What other components do I have, right? Well, I have this tree node, right? I have this answer, right? So what does this answer mean? This answer means that we're able to get this answer, right? Because this green answer is just equal to the blue one minus the red one, right? See what I mean by it's visual. You just kind of you have all these components and you just try to add them, remove them, and so forth, right? Okay, so then now let's just say you're able to combine them, right? Then if you're able to combine them, then now your red pieces is maybe something like this. And then as a result, then now you can just recalculate what the parent is passing in and then figure it out, right? So then now you have this one that you're trying to figure out, right? Yeah. And this one, of course, is just, well, the whole subtree minus this subtree, right? So that's kind of the idea. But if you kind of try to do this for every node, then, well, you have to kind of keep going up. So there is a better way to do it, and this is where the rerouting idea comes from, because otherwise you have to keep going up to... Excuse me, hang on. Apologies, friends. Been kind of sick the last couple of days. Still have sore throat. Still recovering. So the last part about tree rerouting is that you actually pass in the answer from the quote unquote the answer component from your parent, right? So the observation here is that, okay, let's say, let's just say, the difference between this answer and this answer is just equal to as we said, there's some stuff like this, trying to find that piece. So, okay. But the input coming from the parent, right, that we can kind of, what is the delta, right? So instead of calculating all this stuff again, we can just say, okay, well, this node already gives, we already have an answer coming from this node, or we pre-calculate this answer, and then so that when we go down the tree, we already have the answer, right? So we don't have to kind of take the component. And then now, if you kind of think about it, well, if we try to go down this layer, well, what's the difference? Well, the difference is actually pretty simple, right? It's just kind of, like I said, one is this component, but to kind of pass in, so we have to do some maths there. But it's also, well, this component we already know the answer to, so then it is just, you do some calculation to get the answer close. The delta for these components, now that you move one more. I know I said that in a very weirdly specific way, but that is general. And the reason is because I just want to generalize this particular piece for a second. For this particular problem, it just means that for every node that is the same color, right? That means that, let's say in this case, there are two nodes that are the same color, and which kind of calculate for purple. The two nodes, when we kind of pass in here, maybe has a cost of, in this case, for this particular node, it would have the cost of 1, 2 plus 1, 2, 3. So maybe this is 5, right? 5 and the two nodes, right? So cost is equal to 5, node is n is equal to 2. And then when you go down, well, we just have to recalculate everything, right? Let's say we do the math here, and keeping it simple, this is actually 0 because none of this is purple, right? But when you go down, that means that there are two nodes, so that means that even though this cost is currently 5, going down will increase the cost even without additional nodes because those two nodes got further away. So that means that now passing it down is going to be 7, 2, right? Meaning that the total cost from the parents, and now that already factors in that as well, it's going to be 7 with two nodes on top. And of course, you can, there are different scenarios. Like for example, if this node is colored, then you still got to do some maths, and then you're like, okay, well, there are now 3 nodes, and they're all one step further, so it's gonna be 8 or something. I don't know, maybe I did the math wrong, but well, I definitely did the math wrong, because here then, well, that's the parent going in, but you have to do the math for there. But yeah, I mean, whatever the answer is, 1, 2, 1, 2, 3, 3, 4. So 2, 4 is not. Oh man, not a good talking time, right? And that's basically the idea for this problem, right? I mean, in terms of actual implementation, we'll go over the code, but that's kind of the idea that, in terms of visualization, how you get these rerouting problems. I'm still kind of just finding my legs on it. It's been a while, but that's the thing, right? Is that if you really learn these algorithms correctly the first time, and you kind of see the visualizations that I was able to come up with, well, because I do have the visualizations, those are for me anyway. Easier to retain, more difficult to lose, and I'm able to kind of redo them from first principle. Will I be as fast as someone who was practicing this yesterday? No, probably not. But, you're still able to get it. You're still able to figure it out. You're still able to work it out. Right? Even if, sometimes, that's it. Anyway, in terms of code, though, yeah. We'll go over it. Okay. And even then, if you watch the live portion, I did make a lot of mistakes and silly kind of, just silly everything everywhere. So definitely, yeah, you still have, you still need to practice the implementation, but you're able to figure it out because the idea is much cleaner. First, I converted to adjacency list. I'm not gonna go over this. This is a hard problem. You should have the idea. This is just giving me for each node. This is a regular tree traversal recursion, really. There's a node, there's a parent, except for that there's a color. And for that color, that's the only thing that we care about. There's the total cost of this subtree, right? There's the count. And then, if this is the same color, then there's 1, right? And it's at the root, so the cost is 0. But we add the count. And this is just recursion. And then after the recursion, we know that V is populated, so we just sum it up to get the total count of the subtree and the cost of the subtree, right? Oh, jeez. I was doing well on the other videos, but I think it's just too much talking for a bit. Okay. Right, because the cost is either the cost of the child, but now everything in the child is going to be added by 1 because they're now 1 more distance away. And that's really, I know that I'm like trying to draw these visualizations as I'm kind of talking about it, but that's how I think about it, right? So that you can work out, like, because it's kind of, if you just look at just the code, it may not make sense, right? So this is like the new added distance for the answer that are going to that branch. And then F2 is just almost the same thing. So the cost too. So for each node, the cost is just the cost of the subtrees, right? Subgraph, subtree, plus the cost of the parents, right? So that's basically it. So this is done for itself. The thing is that you have to calculate the P cost and the P count. P cost is the parent cost. I write stuff that are kind of like this, where it's just the cost from the parent side, and in this case, I also add a count, which is count from the parent side. Honestly, I don't know if this is a standard problem or not, and maybe there's a cleaner way of writing it. So it may be that it may come out that I wrote this in a really dumb way. But some of it I consider beauty in that it also means that you can come up with this too, right? And then you have this like really weird formula, so we'll kind of rewrite it a little bit. But yeah, so new node is you go to count sub node is this is the subtrees count of new node count. Whoops. This is the subtree, right? So then plus p count, right? Because this is just the number of count from the parent side, so you just kind of bring it back in. But this is the count of the subgraph. This is not new node. Maybe no children count. No children parent count. Okay. And the way that I even this maybe it makes it a little bit awkward. The way that I would think about it is just to I don't want to do this for you because I think you really should do this, like for tree rerouting problem. And once you do it a few times, it becomes more intuitive, and you can kind of see it without drawing it out every time. And I don't know. I think every time I say something like that, when I don't give that as an explicit instruction, people are like, oh, why don't you just draw it out? I'm like, are you here? I mean, if you're here to watch for entertainment, that's fine. But if you're here to learn, you still have to do work, right? It's not like, it's not like, you go watch people playing basketball. You don't think you got better at playing basketball just by watching. No, you still got to go and do it, right? It's okay. I trust you. You can draw these things, right? But yeah, the way that I think about it, count sub node minus count sub v. This is the new. This is basically the way that, like, if you kind of think about the tree that we already drew. These are the number of nodes. Maybe I'll just annotate it. Whatever. So this is equal number of nodes that does not connect to V, right? So that means it's just if you kind of think about a node and then you go down a tree, then it contains all the other subgraphs, right? So it's just all the other nodes with the same parent, right? Right, and then p count is just, well, if you think about it, then there's all the other stuff is all the other nodes, and then p count is just all the other parents. So it's basically like all the parent e nodes for your parents, so you kind of inherit them as well, right? So that's kind of the new p count, the parent side count, if you will, or whatever. I don't know the terminology, and that part actually is the easier one. So I hope you're following along. And then now we have to update the parent cost, which is the tough part, right? So this is, I mean, and I say this, as someone who, if you watch the live one, I messed this up. I mean, it looks very, I don't even know if this is, I don't even think I consider this clean, but it's just short, right? It's a 4-liner. It's ridiculous. But if you watch the live portion, you'll see that I screw up a lot with this one. But anyway, I'll break it down though. So cost of node is going to be, the cost of these nodes, right? Of this subgraph. So we want to do cost of node minus cost v plus count of v. So this is the cost of your of this node's of the children's parents other children's. So maybe another way to think about it is that these are the costs. So by taking your parents' cost, because now we're going one layer down, so we're going to children. So by taking the parents' cost subtracted by your cost, you're getting the sum of all your siblings and your parent, right? Again, try drawing this out at home, right? So you could say maybe a node's sibling nodes plus the parent. So the cost, that's the cost, and plus count of v, because, well, because for this particular, because this is your contribution, and your contribution got one step further. So when you subtract it back out, you have to subtract out that one step farther, and and this is the contribution to that, right? You could also look at this as the opposite of when you calculate it here, because that's your subgraph's contribution to the cost of the contribution for the parent node, right? Okay, p cost plus p count. This one looks awkward still, but is more straightforward, honestly, because p cost is the parent's cost. So we kind of, so to bring it down one level, we add p count, because there are p count nodes, each one step further away as we go down, right? Gotta clean my monitor. So that's basically what this component is for. I also, by the way, I also realized that I can separate or like merge these out, if you will. but it's fine. But yeah, and this part, it is just maybe I should put them like I don't know. I don't know if this is much cleaner. Really, it is very confusing. But basically, this is I kind of wrote it in a weird way actually. But if you watch the live portion, you'll see why kind of, because I kind of went down the wrong path. But this is the parent plus sibling nodes. They are now one more step away. The number of parent plus sibling nodes. Sibling nodes is not quite sibling subgraphs, let's say. Maybe that's more precise. And the same for here. Let's just pretend I changed it. Because it's not just, if you're on a tree, it's not just your sibling, but it's actually the number of counts on all the, like the total subgraphs of those siblings, right? So, but basically, all the counts means that for this component, the cost of all the parent and the children, it actually increases by the number of count, because the number of nodes, whatever that is, got one more step away, right? So that's basically how I came up with this. And that's it, right? And it just kind of works after that. Yeah. The rest is less interesting actually, for at least for Q4, which is that we just kind of make sure, well, one thing is that we don't calculate for the same color twice, right? For obvious reasons, because there are only 20 groups. That should be fine, because that means that we do 20 times n, we're okay, right? So yeah, and I just kind of, yeah. For this particular problem, I actually also, just to, I don't know if there's a cleaner way to do this. Maybe there is, but I just actually, for each node, even if it's not a G, we give you the cost of that node, right? Even if it's not the right color. The reason is so that you could do the tree routing based off each node, right? Assuming that you can. So then for here, for each color, we only add the cost to the color for that node. And that's basically it for the setup. In the end, we have to divide it by 2 because we do the pairs of nodes, right? Meaning that if there's one from 0 to 1, we also calculate the answer from 1 to 0, which is fine as long as it's consistent, because then now you can just divide it by 2. And that's it. That's all I have for this one. It is going to be linear, right? It's just tree rerouting. You could also say maybe it's n times alpha, where alpha is the number of colors, or g maybe for groups for this particular one. So g times n, so it's O of g times n time, and you can say maybe g times n space, though technically O of n space max, but depends how you want to say it, right? And that's it. That's all I have for this one. Let me know what you think. It's a long, tough one for sure. Long, tough explanation, but hopefully if you just watch this explanation once, you are able to solve tree rerouting problems in the future, because it is just, all about that visualization I did in the beginning. And that's it. That's all I have for this one. And you could watch me solve it live, then it can't. Oh, actually, let me show the code real quick. Yeah, this is my recursion code. This is my recursion code with, doing the actual cost, updating the parent, and updating the count. Updating the count should be straightforward, but I think updating parent is also not that bad, but I don't know, I struggle today. But yeah, and this part, not super interesting if you ask me. But that's it. That's all I have for this one. And yeah, you can watch me solve it live in contest now. But, okay, silly mistake, but that's okay. Okay, let's focus now. Q4. Pew did this one. Wow, Pew did this one really fast. And okay. I mean, I don't know. I keep saying that and hoping that they catch the cheaters, but maybe they don't. Okay. You have a tree, undirected, nodes, edges. Nodes, edges. Group. I don't know why I'm reading so slowly. I think I got a little distracted by the last problem. I'm still thinking about it, not gonna lie. Okay, focus. Alright, okay. I mean, this is just standard tree definition, groups of I, okay? U and V are considered the same group if they're the same group, okay? Interaction is the number of edges on a unique path between them. Okay, I mean, that's just... Okay, I mean, that's just like the distance, right? The sum of interaction. So the sum. I don't know what they call it. Why invent a new term if it's just distances, right? Why are you inventing a new term? You're not even like, and everything else is just abstract things anyway. Like, why would you invent a new thing? Okay. So this is and then sum. Okay. Is my n is 10 to the 5th. I'm trying to think. There's gonna be at most n groups, right? Oh, group is only 20. That changes things. I think it's just rerouting, right? Yeah, I mean, I think it's just rerouting. I thought we did a recent rerouting problem, right? Then you do it once for each group. I think that's the idea. Which is why I looked at the group and I was like, well, I don't think you could do it if the groups are big, but okay. And then now, yeah, it's just 1 to 20, right? So, done is equal to set, for I and range of n, is it 0 based? It is. Good. If group sub I is not in done dot add group sub I, and we just yeah, I'm trying to name it honestly, but it's fine. And then we just root it at F, right? Alright, let's actually write it out, and maybe the group ID, maybe that's fine, right? Easy to pass along anyway. Okay, so then we just write out how I usually write these things. Except for usually I don't get it wrong, but maybe I do today. Actually, I get it wrong a lot, but just still not usually. Okay. Okay. How do I write? Okay. I think someone taught me how to write it in a cleaner way. I was reading notes on it the other day, so maybe I'll try as a new science thing. Okay, right. Would I return? Okay, so the sum of all of these, right? So it's not just, you don't have to break them down by group or anything. Maybe something like this. I don't know. It's not quite right. I think it's fine. It's you don't need to be precise. Maybe. I think it's. I think I'll just change it real quick. This is not going to be right. There are optimizations I can make here, but I don't want to prematurely do it. It should be fine. Just 20 times n instead of n. Maybe it's not that fine, but it's a constant cost compared to incremental. There's no complexity wise. We'll see. I don't know. I'm not confident. But okay. So this is fine, right? Oh, there's a peak cost. I guess that's the rerouting thing. Excuse me. I still write it my way, I think, but okay. Okay, so what's the new P cost? P cost is basically cost of 2 of node minus cost of V plus P cost, right? I think maybe that's roughly right. Oh, F2. Alright, well, that's going well. No, it's because I forgot to do, is this plus 1? No, I mean, it is this plus 1, but we have to, I didn't think about how to filter it out. I mean, this part should take care of itself, but this part, actually, how do I filter it out? Huh. So I can just do, I guess it's just like the depth of the thing. Maybe you can. I don't know. Maybe this is awkward. I don't know. If something like that. I don't know if that's quite right. I mean, it's definitely not why you're calling this, but how do you get 9 though? Oh, okay. I mean, so that's a actually not sure. Oh, I think I get it, but something's off. Because it shouldn't be 333, right? Like 0 is 1 plus 2. 1 should only be 2, so something is wrong anyway. 2 should be 3 is fine. So that's why I was inconfident why it is wrong. Okay, start at 0. Node 1 is 1. But this should be minus depth, I think. That's why. And I didn't calculate this cost correctly because we have to shift it by whatever. That's hard. Actually, I thought it would just take care of itself, but actually not the way that I did it this way. It's not that bad. We just have to think. Okay. Maybe? Okay, so because it goes to 1, and then now no, I think this is fine. Okay, maybe not, but now we have to use it. Cost of 2 is that even true? Oh, this probably could be true actually. Yeah, but we just have, but this updating is not true. Okay, so this minus these, which is probably fine, plus p cost. Maybe not so fine. Maybe I have to do a p count as well. P count, it's just going to be counts of node minus counts of we. Okay, so that's the number of nodes. Including this node. Okay. Plus p count for other parent counts. Right. And then now p cost is the parent cost, but every time you do it, you have to plus p count for one step further. Something like that. But I don't know how that would fix. Oh yeah, right. But I don't know how that would fix Yeah, this answer, because it's just would give me more if anything. I mean, I think the idea is right, mostly right. Maybe, maybe not. I'm not doing it right. That's for sure. How do I handle this phase for the cost? So with nine things, we don't care. This seems maybe okay. This only works for the root though, right? Maybe. Okay, let's actually print this part out. Maybe we could see for ourselves. Okay. For 0 is fine. For 1, G is okay. G is fine. P cost is 0. Yeah, okay, because that's nothing else. P count is 1. That's true. Is it true? Yeah, because it counts the thing, right? So then 1 is going to take the cost. P cost is actually 0, so cost of node is already wrong, maybe, because it's at 1 distance away plus 2. Okay, now I actually did this as a hack because I didn't have counts, but I think I could just use counts actually. Because then now plus count sub 3 because they're all 1 step further away. Okay, we don't need D anymore. Okay, now you're just still going crazy, but that's even more crazier, really. I don't know how that got worse actually. Okay. Okay, no, the P cost is 2. What's the actual cost? Well, I feel like this should not be hard, but I am not doing well today with this one. Okay, 3, 1, 0. That looks right actually. So then so this cost is the parent cost. Maybe I'm off by 1. Okay. So it goes cost is 1 plus P cost. P cost is 2, which is wrong. P cost should be okay. So this cost is 3 minus 1. Well, 1 is just wrong, right? Oh, I think this also has to be okay. That is funny that ironically by adding a cost it subtracts it out enough. Okay, why is this so big? I thought I don't know what I'm printing anymore. Maybe oh, that's just the input. That's not part of the cost. Okay, so this is actually okay, so the cost actually, maybe that is off. Anyway. Because it doesn't count distance to itself, I suppose. Okay. So then now this is 3, 1, 0, 0, but then now 3 minus 1. How does it know? Oh, the subtraction from the V part. Okay. So this part is wrong. Is this part... This is the cost plus count sub 3. 311 is still wrong though. Because this is this cost contribution because we have this thing. And then now P count. I mean, this is 1 is wrong, right? Okay, P cost is 0, which should be right. By itself has to plus P count. I think this should be handled here. So something here as well. Oh, no. Okay, so count of node is going to be 3. This is 2. P count is 0, so this should be just 1, right? And there is only 1. So that's right. It is right, but this thing doesn't... P cost does not factor in because this P cost should be 1. P count does not factor in. No, the P1 is right here. Okay, so so this is the right P count, but the distance is messing up by not counting it. Okay. I mean, I don't want to guess, that's why. I mean, I'm trying to reason it out. So, okay, so this is the contribution. This is the P's contribution. But it doesn't have the contribution for the node itself. Which I guess we just have to do. I guess it is just this part of it. Okay. All right. Group sub. I think that's enough because this should factor that in, but it's just one more distance, right? But then now this is right, but this is really wrong. This should be a basic one for tree rerouting, but I am really messing it up. This was not enough. Okay, so why do I have 4 here? I have 4 here because P count is 1. This really could be a, just n minus count. I don't need to pass this actually. Yeah, just have one fewer thing to do. Well, we can check it actually. Well, it's not just n. I don't know. Why should we 3 2 3? So peak cost is at 4, which basically seals this thing. Okay, so this is 0. Oh, this is maybe this doesn't have a peak cost. Oh no, this is just to pass in the peak cost. Okay. Is peak count correct? Then peak count seems to be correct here. So it should be correct or up to date. So okay, so this is what is this? Why did I have cost 2? I'm trying to figure out why I have cost 2 here. Did I fix it? Maybe not, but I fixed the first one at least. Because 323 is what I was looking for. Why did I have cost 2? Cost 2 is the cost with the parent. Why would that factor that in? Because you already factored that in here. Could I have used that way instead? Maybe there's a formula with that instead. But, yeah, okay, well. Is there a formula with that instead that makes it easier? Because it's still wrong. But I mean, this one I knew it was wrong because we have to divide it by 2, but the other one doesn't really match up. Even this one should not. Oh, that's okay. Actually, I forgot. I wrote it this way so that I can so I could be lazy, and then I just was too lazy. Okay. Okay, now everything's divided by 2 above, so then we can just divide by 2. Is that good enough? 4, 2, 3. I honestly I don't know. I'm going to do an optimization. So that was just a silly mistake. I can't believe I messed up a for loop. But yeah, maybe what I could do is I don't feel so good about how much space I'm using or time I'm using. So I could YOLO submit, but this should be like 2 minutes to add, so we can play around with it. We could theory craft later. Yeah. Yeah, we could do it this way just to get the first one, whatever. That's fine. And then here we go for J and GS of group sub I. I think that's why I kind of wrote it this way, but oh, not a range anymore then. Okay, is there a timing? Oh no, it's just fast. I do still have print statements that I definitely need to get rid of before it gives me other errors. Where's my, okay, there it is. That would be funny if I just took a long time because I had this confusion. Okay, well this is just wrong as well. This is the same input as before, so I mean it's example 1, slightly different. So okay, so there are definitely still things that are, oh no, it's not the same. What's different? Wait, oh no, this is 4. Let me read this one. What would be, why is this different? What, well, I mean it's the same, so it should be 4. Well, why am I different? That part actually makes no sense. The peak cost should be the same from 1 and, so the peak cost is different and therefore just wrong. That doesn't even make sense. Why would it be different? That doesn't make sense. Isn't this the same for, well, oops. Okay. Fair enough. Oh no, I was looking at the, was I looking at the wrong case? I guess I was just looking at one case. This is something different. That looks very similar to what I would have want. This is still wrong though, of course. But at least the peak cost is consistent. Okay, so 1 P, other P count is just fine. P cost is clearly not. Okay, so the cost is 2. Minus this thing, which is, this is going to be 1, this is going to be 0, so this is 2, so this is 1 plus so this is 2, but P cost and P count, which is true. This is a little bit wrong then, but how? I mean, it's definitely wrong on this part because there's no, this part should not matter. Or the D part is pretty straightforward to understand. Why is this wrong? We subtract 1. But is that the contribution to the answer? For cost 2, it is. So the other map is going to be 1. I see. I see. I think the way that I should write this is actually plus and now we don't have to worry about D. Yeah, I think I didn't do the distance formula right for the extension. This is none of this extends to the distance. This extends all the distance of the nodes by 1. I thought pcount would do it, and pcount does do it, but only for the pcos portion. So that's how I figured it out. Now is it right? I mean, it's slightly closer. Wait, let me double check the input, because that happens to me sometimes. Okay. I mean, I was imprecise. That's definitely not right. So, and I think the D was my way of doing it, but I didn't really think it through a little bit. I mean, I know that I got accepted. I just didn't, or I thought about what if it was for that particular node, and it always felt a little weird because that felt weird for sure, which is why I was very quick to get rid of it. Once I realized that this is how you represent the number of nodes that are not in the. I mean, everything makes more sense once you visualize it, and I'll go over the explanation in the explanation video, which, depending on where you're watching this, you know, maybe either you already seen that part of it, or you know, if you're just watching the contest video, then well, wait for that part of it. But yeah, because this is just all the other things that are not in the parent. And then once you figure that out, I mean, it's not hard. It's just, it's almost like a tricky case analysis, and I probably could have written this out to be not a one-liner. That would make things a lot easier as well. Pcount also doesn't need to be a pcount really. I mean, it does get used here, but like I said, pcount could be a calculated value. This just, and the reason why I don't like it, even though we had to think about it, and it's correct, is that, well, you have to think about it and you have to verify that it is correct. Yeah, okay. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, everything in between. Stay good, stay healthy, good mental health. I'll see y'all later and take care. Bye-bye.